Hello and welcome to Engineering Economy. This is Dr. Ola Kamerdiner. We will talk today about interest and equivalence. Specifically, we will talk about a very important concept of time value of money. We will also talk about interest calculations, cash flow equivalence, and single payment compound interest formulas. Our objectives for today is to learn the following topics. We will be able to understand the concepts of time value of money. We will also be able to distinguish between simple and compound interest. We will understand the concept of equivalence of cash flows. And we will solve problems using single payment compound interest formulas. So let's start talking about how to compute cash flows. So quick question to you. Would you rather receive $1,000 today or receive $1,000 10 years from today? Of course, for most of us, the answer is $1,000 today. Why? Well, for example, I could invest $1,000 today to make more money. Or I could buy a lot of stuff today with $1,000. Who knows what will happen in 10 years? So the question again, right? Would you rather receive $1,000 today or 10 years from today? There is a time value of money. And that is, most of us would answer that we would like to have it today. Money is a valuable asset and people would pay to have money available for use. The charge for its use is called interest rate. So the question is, why is the interest rate positive? Well, there are different arguments. First argument is that money is a valuable resource which can be rented, similar to an apartment. Interest is a compensation for using money. There's another argument. Interest is compensation for uncertainties related to the future value of the money. Because money is more valuable today than in the future, we need to describe cash receipts and disbursements at the time they occur. So again, very important to realize it, right? By answering the question today, we are showing that we value the money today more than the monies that we would have in the future. So the cash flows of two payment options. Here we can purchase a new $30,000 machine as follows. We could pay the full price now minus 3% discount, or we can pay $5,000 now, $8,000 at the end of year one, $6,000 at the end of each of the next 4 years. So if you pay in full, these are our cash flows. So again, it's 30,000 minus, as you remember, 3% discount, right? So 3 multiplied by 30 is going to be 90, not 90, sorry, it will be $900. So therefore, right, from 30 we're going to subtract $900. We'll get 29,100 that we would pay now if we pay in full. And then we won't have any payments in the years 1, 2, 3, 4, or 5. Again, remember, we're using the end of the year assumptions. So if you plotted a cash flow diagram, the cash flow diagram would look as follows. We would have this arrow pointing down because we have a negative cash flow, and the timing of this cash flow is at time now, which is year 0. So again, there's a second option that we can do. We could pay it in 5 years rather than paying it in full. And then we would have the following cash flows. We would pay now $5,000 year one, at the end of year one, we would pay 8,000. At the end of year two, we pay 6,000. At the end of year three, we pay 6,000. At the end of year four, we pay also 6,000. And then at the end of year five, we also pay $6,000. So notice, right, that if we just sum them up, right, we would have 6 times 4, 24,000, and then 5 plus 8 is 13, so 13 plus 24 would be $37,000, right? However, we can't sum, it's important to realize that we cannot simply sum these. We would need to take into account that 6,000 in the end of year 2 is not the same as 6,000 in the end of year 3. And so we can't really sum them up directly as I just did. However, we can draw a cash flow diagram to visualize these cash flows. So let's do that. So what do we have at year 0? Will we have a positive or negative cash flow? We have a negative cash flow, right? That's 5,000. So we're gonna draw an arrow pointing down like this. Then at the end of year 1, we're gonna draw a cash flow arrow that represents 8,000. So it's gonna be longer than this arrow. It will also be pointing down like this. And then we also have at the end of each of the other years, 2, 3, 4, and 5, we have the arrows pointing down representing 6. So they're gonna be right between 5 and 8 in terms of their length. These are our errors representing $6,000 that we paid. So now let's take a look at the example where we have a cash flow for a payment of a loan. To repay a loan of $1,000 at 8% interest in 2 years, we can repay half of $1,000 plus interest at the end of each year. So this is what would happen then. So we're getting the 1,000, right? We're borrowing 1,000. This is our balance. So we receive a positive cash flow from borrowing $1,000. Again, remember, as I mentioned in the previous chapter, we always need to take a perspective of a specific person. We can switch the perspective. So now we are assuming we're borrowing, right, $1,000. So from our borrower perspective, we have $1,000 that we received, and then we're going to be paying it back. So we're going to pay back a half at the end of each year. So we're paying back 500 because it's a half of 1,000. But we also need to pay the interest. We had throughout the year 1, we had this balance of 1,000. So at 8%, right, the 1,000 that we had accrued, 1,000 multiplied by 0.8, which is $80. And so you can see here, this is our interest. So we would need to pay not just the balance, we also need to pay the interest. So together, we would have 500 plus 80, which is 580, and we're paying it, so it's a negative cash flow. So again, at the end there, right, we're going to pay again another 500. The balance is going to reduce to 0. But during the second year, we had this balance of 500. So 500 we will need to multiply by 8%, and that will give us 40 in terms of interest. And so we have 40,000 of interest, and then we paid off the second half, which is 500. So 500 plus 40 is going to be 540, and that's our payment. So we're paying, so we are taking those money out of our account, right? So this is negative cash flow for us. So we could visualize this as follows, right? This would be a 0 at 1,000 at a time 0 pointing up, arrow pointing up, and these two will be arrows pointing down at the end of year 1 and end of year 2. So here's our cash flow diagram. Arrow pointing up for $1,000 we received at the beginning, and then 2 arrows pointing down at the end of year 1 and end of year 2. Notice they're not the same length. This is slightly bigger because here we have 580s that we have to pay, while here we have 540s that we have to pay. So now you can see, right, if you look at these cash flows, again, we can just sum these cash flows together. As a matter, the 1,000 now at 8% interest is equivalent to these cash flows for years 1 and 2. And so let's talk about time value of money again. Money has purchasing power. Money has earning power. Money is a valuable asset. People are willing to pay some charges, which are known as interest, to have money available for their use. So let's talk about two kinds of interest: simple interest and compound interest. Simple interest is not used very often, and that's an interest that is computed only on the original sum and not on accrued interest. So the total interest earned is simply principal multiplied by the interest multiplied by the number of periods. So again, this formula is used very rarely because not often that we actually have simple interest used in practice, because the simple interest does not accrue, the interest does not accrue interest in that case. So again, P is the principal or the original sum that is borrowed, and then I is the annual interest rates, which is simple interest, and then is the number of years. So once again, it's not going to be very often that you will use this, maybe just for this lecture altogether. But we need to know, right, so that we are able to distinguish what type of interests there are. So simple interest is not a typical common interest. And according to that interest, the future amount of money that we would get, right, would be found using this. P, which is original sum of money, plus the interest. And the interest is, total interest is P multiplied by I multiplied by N. So again, F is the amount due at the end of N years if we're borrowing P, right? So here's an example of a simple interest rate calculation. A loan of $5,000 for 5 years at simple interest rate of 8%. So what we want to do is we want to find what is the future amount at 5 years using the simple interest. Again, simple interest is not going to be found very often. So for most of the problems, you can easily assume that it's not going to be a simple interest. And unless you actually read in the problem where it says simple interest, you would always assume compound interest. So using the formula, we can find total interest earned, which is P multiplied by I multiplied by N. So this is our P, right? That's the original loan. So at first we borrowed 5,000. We borrowed it for 5 years. That's our N. And the simple interest is I, which is 8%. So using our formula, we get $2,000 of total interest earned. And then the future amount is then the principal plus the total interest. So it would be 5,000 plus 2,000, which is 7,000. So that's the amount due at the end of the loan, $7,000. So when the interest does not accrue the interest, that's the case of simple interest. In this case, you are better off to pay the loan at the very, very end rather than paying it sooner. But the compound interest is going to motivate you to pay it off sooner rather than at the very end of the loan. So let's talk about compound interest, because in reality, most of the time we're going to deal in practice and in this course with compound interest. Interest is computed on the unpaid balance, which includes the principal and any unpaid interest from the preceding period. So that means that the interest that we didn't pay before, it's also going to accrue interest. So the money grows much faster using compound interest. No wonder it's used the most often in practice. Again, in terms of solving the problems in this course, unless you specifically see the problem saying simple interest, you gotta assume that it's a compound interest, even if it just says interest and doesn't say anything else. If it says interest, it means compound interest, unless right before you see simple, then it's simple interest. Common practice for interest calculation, unless specifically stated otherwise. So here's our example of compound interest calculations. Again, the same loan of $5,000 for 5 years at interest rate of 8%. Notice it doesn't say compound interest, but it doesn't say simple. Therefore, we assume it is compound. So the only difference, it doesn't say at simple interest. It just says at interest rate. And so that means it's a compound interest here. And so let's take a look and see. Recall, when we did the same thing for simple interest, we got $7,000 at the end of the loan. Let's see what we're gonna have if we don't use a simple, but instead use a compound interest. Well, this is different years, years 1, 2 through 5, right? And this is balance at the beginning of the year. Notice, at the beginning of the year 1, we have 5,000, but throughout the year, we accrue interest on this entire sum of money, which is 5,000. So we just multiply 5,000 by 8%, and that's $400. So adding these together, the balance at the end of the year is $5,400. That's also the balance at the beginning of the year 2, right? Because the end of the year 1 is also the beginning of the year 2. So then, if we didn't pay it off at all, none of this is being paid off, then we have to multiply this amount by 8%. So multiplying $5,400 by 8%, you'll get $432. So then we adding the balance at the beginning of the year plus the interest that accrued during year 2, this here, and that adds up to $5,832, and that's what we have as the balance at the end of the year 2. And that's, of course, is the same balance as we have at the beginning of the year 3, right? Because the end of the previous year is the beginning of this year. So then, again, we multiply this by 8%, and that gives us this, and then we add these two together to get the balance at the end of the year. And again, this is the same as this balance at the beginning of the year, which keeps accruing the interest at 8%. So multiplying this by 8%, we get the interest amount during the year 4. We add these together to get the balance at the end of this year. And then that's our balance at the beginning of the year. We multiply it by 8% to get the interest in year 5. Adding these together will give us the balance at the end of the year. So notice, at the end of the year 5, using compound interest, we get $7,346.64, which is much more than just $7,000 that we got when we had the loan at a simple interest rate. So notice the compound interest rate gave us a much larger amount that we would need to pay at the end of 5 years. It's amount that's $346.64 more than the amount that we would have paid using simple interest. That's very important to notice that. Again, why this happens is because the interest that we don't pay, it also accrues interest when we're using compound interest calculation. Now let's take a look at the example of repaying a debt. So we're going to repay a loan of $5,000 in 5 years and interest rate of 8%. So we could actually repay it in a different ways. Plan 1, we're going to pay $1,000 principal plus interest due. So what is going to happen? Well, again, we're using the same calculations. The only difference is now we're going to pay off $1,000 each year. So that's going to reduce our balance at the beginning of the year. And we also will pay off the interest. So that also reduces our balance at the beginning of the year. So what are we going to do? Well, first we're going to start with $5,000 at the beginning of year 1, which is year 0. And during the first year, we get an interest of $4,000 by multiplying $5,000 by this rate of 8%. And so the balance at the end of the year is $54, just like in the previous example. However, we say that we pay $1,000 plus any interest due. So we pay the full interest and we also pay $1,000 off. So our total payment is $1,400. Therefore, we're not going to have this $5,400 balance at the end of the year for the beginning of the year. We paid off, right? And so it reduces the balance at the beginning of the year because this is the payment that occurs at the same time as the end of the year. This $1,400 reduces the $5,400, and so we actually have the $4,000 at the end of the year. And because we have the $4,000 at the end of the year, that's also $4,000 at the beginning of the year. So now we calculate the interest on only $4,000 because that's what we have. 4,000 multiplied by 8% is 320 in terms of interest. So we're adding these together. That's going to be 4,320 at the end of the year. But we're going to reduce it because we're going to pay off the interest amount of 320, and we're going to pay off the principal payment of $1,000 as agreed. So altogether our total payment for that year, and we pay it at the end of the year, is $1,320. So this 4,320 is reduced by this. And when we subtract these two, we're going to have 3,000 left. So we actually have 3,000 as a balance at the beginning of the year. So then this is what accrues interest, and we multiply it by 8%, we get 240. So together, when we sum these two, we get the balance at the end of the year. But we're going to pay off, at the end of the year, we're going to pay off this interest payment in full. So we pay off the 240 in full. And we also pay additional $1,000 of principal. So we pay the $1,000 of principal, so together, this is our payment at the end of the year 3. And together, this is 1,240. So this balance at the end of the year is actually reduced by 1,240, and so we only have 2,000 left. So we have 2,000. This is the interest on 2,000. This is the balance, and we paying the full interest, and we paying 1,000 of principal. So that's our total payment, which reduces this balance to just 1,000 at the beginning of the year 5. So multiplying 1,000 by 8% gives us only 80 to pay in interest. And so this is our balance at the end of the year. This is our full payment of the interest, and we paying the remaining $1,000. So this is our total payment for that year, and notice that then it completely pays off the loan. So the principal payment is paid completely of $5,000. This is our interest payment of $1,200. And the total payment is together the interest and the principal, which is $6,200. So that's according to plan 1. But we could have a different plan, right? There's always going to be a plan B. So what's our other plan? Well, there's actually many plans. So one of them is to pay interest due at the end of each year, and the principal at the end of the 5th year, right? So we paying only the interest due each year, and we paying the interest in full at the end of 5 years. So what are we going to have then? Well, the interest will not going to change because we're not going to pay anything off of the principal, so the interest will remain. We only pay off the interest payment. So the balance will always stay at 5,000 because we pay off the interest in full. But we gonna pay the principal at the very end there. So the interest payment is gonna be 5 times 400, which is 2,000. We have the principal payment, and we're gonna have the total payment of 7,000. So notice we didn't use the simple interest rate, we used the compound interest rate. But because we paid the interest accrued that year every year, we never accrued interest on the interest. And so it's almost like paying a simple interest as long as we pay off all the interest due that year. Now let's take a look at a different plan. We have plan 3. We can pay in 5 equal end-of-year payments. So these 5 equal end-of-the-year payments, they will distribute things as follows, right? This is gonna be, this is gonna be our total payment. So every year we're gonna pay 1,252, and at this point you don't know how we got this, but later in next chapters I'll teach you how to get this payment calculated. But we have this payment of $1,252 $1.28 that we pay every year at the end of the year. We have this as the beginning principal, right? So at the beginning of the year 1, this is what we have. It accrues this interest simply by multiplying it by 8%, multiplying this 5,000 by 8%. So together they give us the balance at the end of the year. We're gonna pay the interest payment 400, and whatever is remaining here is gonna go towards the principal payment. So then we can subtract this principal payment from the 5,000, and that gives us this balance at the beginning of the year. Or alternatively, right, we could just take, this is the balance at the end of the year, we're subtracting this total payments that we had. So subtracting from 5,400, subtracting 1,252.28 will get us 4,147.72. And so again, now, right, if you multiply this by 8%, this is going to be the interest. And so adding these together gives us the balance at the end of the year. We're going to pay this whole interest, and whatever is left, right, out of this 1,252.28, this is going to go towards principal. So notice here, right, the interest payment is going to decrease, and the principal and payment that goes towards the principal is going to increase. While previously, right, we had interest the same, and there was nothing going towards the principal in the previous plan. So now when we added these, we got 6,261.41. And there is a fourth plan. We can pay principal and interest in one payment at the end of 5 years. So notice what happens is that here we just let the interest grow and did not pay any interest, do not pay any principal until the end of the 5 years. And so that actually gives us a larger total payment, right? We can compare. So this is over 7,300, while the previous things that we see, right? Here we have a little over 6,200. This is 7,000. And the first plan is 62, right? So this is exactly 62. So the very first plan is the best out of all of them in terms of the total payment. However, right, they're all basically equivalent. They're just different ways to use the money, but in terms of the total payment, that would be the smartest way to go. However, right, we are not taking into account the time value of money in this case. If we're paying there in the first plan, if we're paying the interest and the principal payment, we pay a large amount towards the principal payment every time, right? We are not using it for something else. If we are out of that $1,000, we can't use it. While here, right, we could still probably use it for, and again, it depends, right? All of these different ways are equivalent. However, you know, we might prefer one or the other depending on our individual circumstances. So if our interest is to minimize the total payment, right, then we know which one we would prefer. But if we want to do something else during that time with the money, right, it might be the one that actually doesn't minimize the total payment. So let's take a look at even closer look at the four repayments. There are differences, right? The differences are in the repayment structure. Repayment amount at various points in time. Also, very importantly, total payment amount is different. Very different. We just looked at that together. But there are also similarities. All interest charges were calculated at 8%. They all achieved the same purpose of repaying the loan within 5 years. And so now let's talk about the equivalence. If a firm believes that 8% was reasonable, it would have no preference about whether it received $5,000 now or was paid by any of the four repayment plans. So that's a concept that is often very difficult to grasp at the beginning, but this is a very, very fundamental concept that we will use throughout this class. So once again, all these different cash flows are equivalent. So if a firm believes that 8% interest, compound interest of course, was reasonable, it would have no preference about whether it received $5,000 now or was paid by any of the four repayment plans. The four repayment plans are equivalent to one another and to $5,000 now at 8% interest. So let's talk about the use of equivalence in engineering economic studies. Using the concept of equivalence, one can convert different types of cash flows at different points of time to an equivalent value at a common reference point. And that is very, very useful because, as I said, we cannot simply add, for the most part, unless we have a 0% interest, we cannot add cash flows that happen at different time periods. So this is a key point, right? We're going to be using the equivalence very often to be able to combine different cash flows at different times and add them and move them to a common reference point in time. Equivalence is dependent on interest rate. So let's talk about single payment compound interest formulas. These are the formulas that help us move cash flows from time now to sometime in the future, or the other way around, from time in the future to sometime now. So here's our notation. I represents interest rate per compounding period. So of course, we're talking about compound interest. N is the number of compounding periods. And P represents a sum of money. F is the future sum of money. So we're going to move from present sum of money P to future sum of money F. So here's our single payment compound amount formula. F equals to P multiplied by 1 plus I to the N. And this is a fundamental equation that allows us to find the future sum of money at N time N based on the interest I, and that is equivalent to the present sum of money P. Alternatively, we could write it like this, right? And even though it looks kind of funny, this whole thing, it just simply represents this 1 plus I to the N. So we will talk about factors. This is the first compound factor. This is a compound factor of finding F given P for interest I at time N. Find f given p at I over n. Here's an example where we can use these formulas. 500 were deposited in a savings account that pays 6% compounded annually for 3 years. We start first drawing the cash flow diagram. Because we talk about 3 years, we also need to include in time now. We have 4 time points, 0, 1, 2, 3. So 500 were deposited in a savings account for 3 years means that at time now 500 were deposited, right? So we have a negative cash flow of 500. So we're gonna have a time 0, we're gonna have an arrow pointing down that will represent $500. That's our P, present sum of money. We want to know how much we can withdraw at the end of 3 years, taking into account that the interest that we get is 6%. So what that means is that at year 3, we're gonna withdraw it. So we're gonna receive something. So it's gonna be a positive sum of money, and it's gonna be in the future. So it's gonna be F with the, and it will be represented by an arrow pointing up. Oops. So this is F. That's what we need to find. So let's go ahead and use the formula now. We have I being 6%, N being 3. So we have F equals P multiplied by 1 plus I to the N. So P is 500. And then we have 6%, which is 0.06. And then N is 3. So when we plug in all the values, we're gonna get this value as a future amount of money. So you can see that we have almost 600, a little less than $600 at the end of 3 years. Alternatively, we could have used this, which is basically the same, right? This is just a factor, compounding factor. And those compounding factors can be found in the tables at the end of your textbook. So you all got your textbooks. So if you open them and scroll to the very end of your book, open them at the end there is a large number of tables that give you different factors for different values of I and N. And there you have, for each page, you have different I, interest rate, compound interest rate. And then as the rows of the tables, you have different N's, different years. It's starting with 1, 2, 3, so on, right? It doesn't have to be years, it could be some other time period, by the way. But different N's as rows. And then in the columns of the tables, you can see different factors. So one of the first factors that are given there is actually factor F given P. So that's where you can look it up, right? So you can plug in F given P, you plug in I and N, 6% and 3. You scroll or you find the page in the textbook that has a table for interest rate I equals 6. And then you look into a row 3 and column that says F given P. And that's where you find this value of 1.191 thousandths. And when you multiply these two, this is what you're gonna get, right? So again, it's equivalent way to different ways to basically do the same. So let's talk about it in a little different way. So let's again look at our notation as before. I is the interest rate, N is the number of compounding periods, P is a present sum, F is a future sum. So single payment present worth formula allows us to find the present sum of money, right, based on the future sum of money. And here we're actually taking this 1 plus I sum to the negative N, which is the same as to say that 1 is divided over 1 plus I to the N. Or alternatively, you could look up the compound factor that says p given f. It's not the same factor as we just used. It's in a different column, but on the same page, right? If we have the same I. And in the same row, if we have the same n as before. So it says find p given f, right? It's not before we had find f given p. This is find p given f at I over n. So here's an example. Wish to have 8,000 at the end of 4 years. How much should be deposited in an account that pays 5% annually? So here we have 4 years, so 5 different time points, 0, 1, 2, 3, 4. We want to have 8,000 at the end of 4 years. So the 800, is it gonna be up or down? We want to have it, so we want to receive it, so it's gonna be up, right? Is it gonna be at time 0, 1, 2, 3, or 4? It's gonna be at time 4 because 4 represents the end of 4 years. So that's our cash flow represented here. F equals 800. What do we need to find? We want to find how much should be deposited in this account. When? At now, time now. So deposited means that we're gonna have a negative cash flow. So it's gonna be pointing down, and this is gonna be our P that we want to find. So let's go ahead and find it at I equals 5% and N equals 4. So we're using the formula that gives us this, or we can use this formula, right? So either plugging in the values directly or looking it up in the tables in the book. And again, we're gonna get the same result. Wonderful. Here's another example. 500 were deposited in a savings account that pays 6% compounded quarterly for 3 years. Okay, is it the same example as we saw before? No, it's not, right? What I'm trying to refer to is this example here. 5,000 were deposited in savings account, pays 6% compounded annually for 3 years. Notice compounded annually. In example 3.5, we had it compounded annually. But in example 3.7, we have it compounded quarterly. So they're not the same example, it's a different example. Because it's quarterly, it's not just from 0 to 3, right? We don't have 4 time points, we have 13 time points. We have 3 times 4 quarter breaks each year into 4 points. So we have at the end of each quarter we need to pay interest. So 4 times 3 is 12 quarters, and we have time 0, right? So altogether 13 time points. So we broke our timeline into 13 time points. So here, each of the time point does not represent a year, it represents a quarter because we're compounding it every quarter, so 4 times a year. So now let's represent where is the 500. 500 comes at 0, right? Because it was deposited for 3 years. And it was deposited, so it was a negative cash flow, so it's going to be pointing down. Here's our 500. Our P. What do we need to find? We need to find how much it is going to be at the end of 3 years or at the end of 12 quarters, which is the same. So that's where we're going to have at time 12, we're going to have an arrow pointing up. That's what we have our F. So now we can use the formulas and notice, right? It's not going to be 6%. It's a 6% that's compounded quarterly, so it's actually going to be 6 divided by 4. So our interest is 1.5 because 6 divided by 4 is 1.5. So here we're giving an annual interest. By default, we're given an annual interest, but we say that that interest is compounded quarterly. So we divide the interest by 4 because there's 4 quarters, and so each quarter we pay 1.5 of this annual 6% rate. So I know it's a little complicated, but I wanted to show you how it becomes a little different, right, when we deal with a different compounding period. Again, I is obtained by dividing 6% annual rate into 4 quarters, and we get 1.5, and then n is 3 times 4 is 3 years, multiplied by 4 quarters per year, so altogether 12 quarters. So then, using the formula, right, plugging in the p, plugging in the I of 1.5%, which is 0.015, and plugging in the n, which is 12, we're gonna get this. So now let's take a look at where we're finding the factors. So I described it before, but just to be more clear, if you find in our book, if you open the page 569 in the 10th edition of our book, you can see the 5%, right? This is an interest, I, compound interest. And then we have our factors in different columns. So here, for example, we can find f given p, right? One of the first examples, example 3.5, and also example 3.7, they used f given p, as far as I remember. And then next to it, we have p given f. And then here we find n, right? For each of the columns, we can find n3, or here, n12, right? So this is how we find the factors. So we look at what factor we need, f given p at 5%, at year 3, we'll get this factor. Or let's say f given p at 12, right? This is gonna be this factor, this value. All right, I hope this was helpful. Keep in mind, right, if we need to find specific factors, this is how we're finding it. So now here's an example of single payment compound interest formulas. We want to solve for P. Here's our cash flows at times 3 and at time 5 at the end of the 5th year. So again, we can't just simply add these together and get a -1,000 and therefore assume this is going to be 1,000. We can't do that. We need to include the interest rate that represents the time value of money. So let's draw the cash flow diagram. So here we want to find the P. It's going to be pointing up. And for year 3 we have 400 pointing down. And for year 5 we have 600 pointing down. And of course this is what we need to find. P is going to be pointing up. And our interest rate is 12% in this case. So now, right, we need to find P. We could convert this 400 to times 0, and we can convert 500 to times 0, and we can add them together. When we convert 400 to times 0, then we convert 600 at time 5 to times 0. When they're both in the same time, then we can add them up. So that's exactly what we're doing. We're taking the 400, that's at times 3, so you can see 3 here instead of n, 12 for I, and we're finding P given f. This is our f, right? It's in the future. We're finding its equivalent in time now, right? And for the present, equivalent present sum of money. And we also find equivalent present sum of money for 600 at year 5. So this is our future amount of 600. Given the 600, given f, future amount, we're going to find its equivalent present sum, P given f, at 12%. And here's 5, because it happens, the 600 happens at 5. So the n is 5 in this case. And why we can add them together? Because this here and this here, they both now at the present time. So at the same time, we can add them together. And that's what we do. We're plugging in, we're finding the 12% page, right? Finding row 3 and column P given f, and plug it in here. And the same here, P given f for 12% in year 5, plug it in, and then adding them together gets us to this. So that's pretty simple. Now here's another example. We want to solve for P the following. But now we're gonna have, right, it's very similar in terms of cash flow, we're gonna have a different interest rate. It's not 12%, it's 15%. So very similar, the only difference is now we're plugging in 15%. Well, it's gonna be a different value, right, because we're gonna have different factors here. Alright, this concludes this lecture. I hope it was useful for you. Thanks a lot, and I'll see you soon.